Hey, welcome everybody to DEFCON 1 Science. We are back. A little bit of a layout today, technical reasons, but since we're going to be screen sharing a little bit, I guess it's not going to matter too much. But with me today is Dr. John Kroon, famous astrophysicist. Well, not too famous, but he will be one day. So we're working on it. We're going to get him some I don't want to say notoriety, but we're going to give him a little bit because, he's going after flat earthers now. So he will be notorious in the flat earth community at least. But anyways, Dr. Kroon, welcome back.
Yeah, it's good to be here. DEFCON 1 Science for the win. It's the awesomest show, or one of them.
It's one of the awesome shows. There's quite a few awesome shows out there lately. I was watching Talk Heathen today. I always add an S. I don't know why. Talk Heathen today. They're a great show. They're part of the ACA, the Austin community of atheists out in Texas, and they have Jamie and Eric. And man, I'm telling you, it's a great show. So shout out to them if they ever watch this, which they don't. They watch other stuff. They don't watch the sciencey stuff, but they should. But if they ever do, shout out to them. But yeah, there's a lot of great shows out there nowadays. So hopefully this kind of fits into that paradigm by taking some of the stuff that people were talking about science and kind of getting a little more technical. And hopefully this show eventually, as it goes along, will fill that niche, kind of so to speak. So anyways, so today we're going to be talking about black holes. What I figured we kind of start into would be basically a basic history of why they think black holes exist, what they are, and then maybe talk about what they are. And then get some questions and Q&A on people's, because black holes are not an easy subject to talk about. I mean, I started reading about black holes when I was in 7th grade, and I thought I had a decent understanding of them until I realized I didn't. They are very complicated, but they are fascinating, correct?
Yeah, awesome. Really interesting objects there for sure. They actually, in my opinion, hold the key to the holy grails of physics, if you will, the quantum theory of gravity, which would be huge for physics at large. It would be a revolution in physics, unlike anything we've ever seen. And if you've ever seen that movie Interstellar, where they're trying to get observations of the singularity to figure out the missing piece for the quantum theory of gravity, and how do you like truly harness gravity and inertial mass and all that's kind of where we are right now. And
I like that movie up to the Tesseract stuff, right?
Yeah, the Tesseract was not yeah,
but I mean they did model that off a real image of what we think a black hole would be. Now the actual images that I've seen modeling are slightly different. They have a little bit of tail to them rather than this photosphere that goes around, but very, very similar. But correct me if I'm wrong, supposedly either near the end of this year or beginning of next year, they actually have direct observation of the either event horizon or photosphere of a black hole coming up, right?
Yeah, it's just called Event Horizon. I think it's next year. And I can actually take a peek real quick. Yeah, it's going to be coming on. I don't know if they actually have data yet, and they're just waiting to like analyze it or not,
They
but
have the data. No,
definitely.
they have the data. They have terabytes worth of data. They are analyzing it, but it's just so much data that they have to go through
Oh
to
yeah,
actually
it
get an
says
image
from
out of it.
2011 to 2017. They use Earth-sized telescopes, interferometric techniques to get radio observations of Sagittarius A star, the one in our galaxy's core. That's going to be awesome. I can't
Isn't it?
wait.
I mean, the only indirect they have observation that they had of them so far. I mean, obviously, if you look in the center towards Sagittarius A, you can actually see the stars moving around, and you'll see them being
Hmm.
affected by relativistic effects. You'll see them do weird stuff like this, and then all of a sudden loop around, which is not going to happen in Newtonian physics, right?
Yeah, I've
So,
seen that anime. Well, it's a video made from mapping the three-dimensional positions and speeds of several dozen stars near the black hole. It's a cool GIF. It's like a little video GIF, and you could see stars like 10 times the mass of our sun being whipped around in their elliptical orbits. And in order to whip a star around at that speed, at that acceleration,
can you imagine
you
the
need some
gravity? It's got to be
insane.
massive, right? I mean, you're moving around a star, right? It's not just moving
Yeah,
around a small moon or even a planet. You're moving around a freaking star. I mean, so yeah,
yeah.
pretty massive. So why don't you kind of talk about maybe the history of the discovery of black holes and why they posited as such a thing must exist somewhere in the universe?
Yes, they actually, although they're often thought of as more of a modern construct, they have a little bit of a history going way back to like 1783, where John Mitchell conjectured that there could be an object massive enough to have an escape velocity greater than the speed of light. And so this was after um, Newton's Principia in 1687, right? So almost 100 years prior, and Newton comes out with the Principia, his laws of motion, as universal laws of gravitation, and he has a iconic picture that shows the Earth and a cannonball, the top of the mountain, and then he has three different trajectories or something. A is you fire the cannonball at slow speed, a low speed, and it goes some distance, hits the ground. Fire it a little further, it goes a little bit more around the curve, and you fire it really hard. You can actually have it come back and hit you in the back of your head, and in which case it will have orbited the Earth. And so when you combine that with his laws of motion, you find that the larger your speed, the for a given body of some mass and radius, like a planet like Earth, for a given mass and radius of that object, there's a unique speed called the escape speed that you would need to be traveling at to escape its. You go off to infinity and you'll have zero speed at infinity. If you go faster than that, you'll have a little extra speed once you get to infinity. You could escape the gravitational binding energy of it. And so if you have an object with that same mass of the Earth but smaller radius, now its gravity is stronger, and you need even more speed. You have to recalculate what the escape velocity would be. And so John Mitchell was just going through these concepts and the math in his mind and saying, hey, um, if the speed of light is x, even if they didn't know what it was yet, they say there must be a gravitational field such that the escape velocity is the speed of light. And so then you go forward in time through the later in the 1700s and into the 1800s, and you see terms popping up in the literature like dark star, and there you have some physicists and astronomers thinking about what these things might be if they're real. So in 1796, Simon Pierre Laplace, French mathematician, there predicted the existence of black holes and said that it's therefore possible that the largest luminous bodies in the universe may, through this cause, be invisible. This cause, he was referring to the extreme gravity, we call that hypergravity today, such that even light bows to the power of this force and will be unable to escape. And then we get Einstein's relativity, and in 1915, his general theory of relativity is published, which predicted space-time curvatures and a new mathematical framework, a new interpretation for for gravity as manifest in nature. And then we get Karl Schwarzschild. He's said to have been in the trenches of World War II, typing in trajectory equations in the dirt for his next mortar launch, and then going off to the side and dabbling in the mathematics of general relativity and hypergravity, and is said to have on the trench lines computed the Schwarzschild radius, which bears his name. So that's kind of fun to think about.
So there was a massive switch in the paradigm of how to think about gravity between Newton and Einstein, right? So Einstein was somebody who came along and said, you know what, Newton works, all this stuff works for certain things, but at certain things it doesn't work for. One of which would be near relativistic speeds, about 20% of the speed of light, or gravity. What actually is gravity? Newton didn't really describe what gravity actually is. He didn't have a really great model for what gravity is. It worked, but it didn't really get to the core of what we think now gravity is, which is a curvature of space-time. It's a metric, right? So would you say that, like, when it comes to a black hole, what's actually kind of happening is if you look at a space-time diagram and you look at the two axes, you have your x and y, where like what's called a time or space-like journey. It's called a Minkowski diagram. If people want to go look it up.
Mm.
When you approach near a black hole, all the space paths actually tend to go to the black hole, and so as you get closer and closer to that event horizon, there are more paths leading to the black hole than away from it. So after you hit that event horizon, all space-like paths all go to the black hole. You can no longer ever leave from where you're at. You're stuck. You're screwed. You're done. Game over, man. Game over. There's no way to ever leave a black hole once you hit the event horizon. Now, depending on the size of the black hole, you might actually survive that, correct? If it's something very, very super massive, you don't have that spaghettification factor, correct?
Yeah, yeah. If you're ever sentenced to death by black hole, and you get to choose what kind of black hole, pick the biggest one in the universe. You could actually live out quite a while as you fall and fall and fall, and then of course, as time dilation hits, you can actually watch the future of the universe unfold before your very eyes.
You would actually see the end of the universe from your perspective. Now, I don't think you have very long though. From what I've read, even with a very, very large size black hole, you're going to die in seconds. But it's,
Hmm.
I mean, I again, that might vary a little bit from your perspective, from what I would call proper time. Once you go past that event horizon, well, first of all, I think you'd be vaporized before you even get any
Hmm.
further, right? Would you agree that the
Yeah,
photosphere is going to you're going to die?
yeah, yeah.
But assuming that you're somehow kind of immortal and you don't have to worry about stuff like thermal energy, and you make it past that photosphere, once you go into the event horizon, I think you're going to pretty hit that quote unquote singularity rapidly. Now, whether that singularity exists or not, as far as an actual object, is there some dispute on that? Because if you look at the mathematical modeling, it exists mathematically, and you could even devise a way to show that in certain types of black holes, if they're rotating and they have some kind of angular momentum and charge, that you have a toroidal shaped singularity. And Paul Davies a long time ago hypothesized that you could actually go through it. Now, I think they've actually
Hmm.
found out that's not actually the case in 30 years since I last read a book on black holes. But I mean, have you heard something along those lines that way back when, that you could actually go through the singularity?
Yeah, I heard about that. I don't know what. Well, one thing that is interesting about that is the toroidal singularity actually starts looking like a string, like the strings of string theory, and how you can have open strings and you can have closed loops, and they think that's why gravity is like 32 orders of magnitude weaker, in a normalized sense than the other fundamental forces, is because the it's a closed loop string that doesn't attach to our membrane of our universe, so they leak into higher
It'd be called a
dimensions.
closed timeline loop, right?
Yeah, well, like the string itself, for like the hypothetical, like a graviton or whatnot, is if it exists in
Mm-hmm.
string theory, it's a closed loop, and so they don't
Mm-hmm.
attach to our
Right.
brain, and so they leak out of there. And then the other three fundamental forces are open, and so they attach and they could anchor down, and so they're correspondingly stronger. And so if you start looking at toroidal shaped singularities, especially if they're really small, or regardless of how big they are physically, because you're talking about a hypercurved
See, I would think
health
they'd be
metric.
imperceptible, right? I mean, I would think that if it's some kind of singularity, again, if you have like an EPR bridge or something, it's going to be on the magnitude of the quantum scale. I can't imagine like a singularity being something you would actually physically could
Yeah,
pass through
right.
anyways.
Yeah, it's going to be. What I'm saying is, it's almost indistinguishable from a graviton string.
Wow. Never
Like
thought about
the
that way.
center of a black hole is just one of these string theory strings for the gravitational force.
Because that would be smaller than a quark, because quarks would be comprised of strings.
Yeah,
So
yeah, it
that's
would be
weird.
super small.
Uh,
But when you get into like Minkowski space stuff and how space itself is already all jacked up, then the question becomes a little more non-trivial.
and with Penrose, I mean, I loved as a kid looking at Penrose diagrams and figuring out how they had that singularity, and then you had space light and time like lines, which would be based upon the light cone from Minkowski space. And I found that to be fascinating. I really did. I was like, man,
Yeah,
what does it actually mean to have a time like journey with no space, right? Because that's
yeah,
what you
right.
would be doing. You would see the entire universe, just the end of the universe, whatever that would be. You would be the only person to experience.
Yeah,
You couldn't tell anybody about it, and you'd be
yeah,
dead pretty quick. But you would see the entire universe die in front of your eyes. Would you not?
yeah. Yeah, that's pretty wild.
It is wild, right? It's almost like this is where science and philosophy meet. This is
Yeah,
where I think philosophy is important. But well, a
yeah,
couple quick questions. People are enthralled by this, by the way. They're asking questions faster than I can ask them.
yeah.
Um, let's see. XXY Charlie or XXSYD Charlie asks, do black holes decay over time? What would be the eventual end of a black hole's lifespan? I'm assuming he's talking about Hawking radiation. So if you want to touch on that.
Yeah, sure. So Hawking radiation, it hasn't been observed yet, but a lot of astrophysicists and physicists, including myself, are I would think optimistic that I mean the theory surrounding Hawking radiation is kind of convincing, but like the as science goes, you don't know till you know, and so we haven't observed it yet directly, but so they decay over very long time scales, and it's also dependent on the mass. You could have it's like an inverse relationship. So if you have a really tiny black hole, like a microscopic one, they're going to decay like super fast, like
And
microseconds.
that's because of the surface area ratio, right?
Yeah, the surface area ratio. So it's going to just yeah, decay away from the nature, that quantum effect of the virtual particles popping in and out of existence. One pair enters the black hole, the other one becomes real and escapes into the universe as lost mass and angular momentum from the black hole. So if you have a larger one, it'll last much, much longer. We'll probably have time in the universe, trillions of years in the future, where all the stars are dead, hundreds of trillions of years, where even white dwarfs are like black dwarfs, and it's just a dark, cold universe, and the only thing that's left is a bunch of black holes, even some black holes that formed in the early stages of the universe.
Yeah, because if you think about it, look at to the outside chat. If you have a very small micro black hole, it's not going to last very long. Its surface area is going to be such that it's going to any virtual particles that are being created from it are going to reduce the mass of the black hole, and it's going to evaporate. That's what it's called, and that's going to happen so quickly that it's not even going to have time to absorb anything or eat anything, like even a proton. So when they
Mm-hmm.
worry about like CERN producing a black hole, which they're not at the energy levels yet to be able to produce a black hole, but theoretically they could, given enough energy levels. But even if they did, that black hole would exist in a picosecond. It would be gone, right? I mean, it wouldn't be
Yeah,
able to even absorb anything to quote feed, where we'd even have to worry about it, and it would decay
yeah.
much faster than a supermassive black hole. Correct?
Yeah. Yeah, but if you look at the numbers, though, it's less likely than Steve McRae materializing on Mars as a giraffe.
Well, at the
Uh,
energy levels they're at now, though, what happens though thousands of years in the future, or even hundreds of years, when we reach higher levels of energy, right?
well, yeah, but here's the thing, though. I don't think. Well, okay, so look at like cosmic rays that are like I think like 14 orders of magnitude,
Some.
12 to 14, like 10 to 12 orders of magnitude more, and they're impinging on our upper atmosphere all the time. They have been since Earth exists, billions of years, and none of those have created a black hole.
But that's low density, right? I mean, the very very high order of cosmic rays are not very dense. I mean, they've had a few of them where they call them like the wow particle kind of
Yeah,
stuff,
there's
right?
the WoW one. Yeah,
Yeah. But by the way, it's weird to think that it has that these particles have so much energy, yet at the same time don't do a lot of damage,
yeah, yeah.
but very energetic. But now, if you had a high density of them, it would it would vaporize the Earth, I would imagine, kind of like
Yeah,
a
probably.
gamma ray burst,
Hmm.
or at least blow off the atmosphere. Next question: explain how there can be different sizes of black holes. Great question. That's from
Oh
Mostly
yeah.
Prophecy. You want to take that one?
Yeah, sure. I'll
Great
say a
question.
couple things about it, and then you can chime in after that. Pretty much. So it all begins with the Schwarzschild radius, which is the sort of the size, if you will, of a non-rotating. Let's just focus now on for now on a non-rotating black hole. That's the radius is 3 kilometers roughly for one solar mass. If you have the sun compressed enough to become a black hole, it'll have a Schwarzschild radius of 3 kilometers, 6 kilometer diameter, and it scales linearly. For every solar mass, you get another 3 kilometers in radius, and so there. Okay, so for things like the supermassive black holes, these are like larger than our solar system because they're like millions of solar masses. And Stephen Hawking has a whole bunch of stuff, a bunch of derivations on why that is. It's all related to like entropy and well, you could just forget about entropy now, or you could think of it as just the fact that the object now has more mass, and so now you have to be even further away, staying under the speed of light to not get sucked in, and so light has to move even further away because it now has more gravitational influence. It's called a gravitational scale radius, so you can normalize it with respect to its mass. Talk about like 3 gravitational radii away, and so forth like that. You want to take it from there? So did you want to get into
You know
entropy
what?
and
I
stuff?
would actually, well, not so much the entropy, but I would challenge people that watch this video in the live chat. You can actually do this yourself. You don't have to have a PhD like he does to actually be able to determine the Schwarzschild radius. It's actually a very easy formula. It's basically
Mm-hmm.
2gm over c squared. So I challenge anybody.
Square root.
It's simple, right? I mean, I've done it before. It's actually 2.95 kilometers is what I calculated, which is,
Sure, yeah.
yeah. So I mean, I've done this personally. It takes a few minutes. Anybody can do it. Go determine the Schwarzschild radius of something. Find the mass. You times it by the gravitational constant, big G, times 2, then divide it by c squared, and that'll give you the radius that object has to be to have that amount of mass in that area space. It works
Mm-hmm.
pretty well, actually. For not, we're going to assume non-rotating, non-charged situation, obviously.
Yeah, so pretty much anyone could derive it too. You got to set the gravitational force equal to the kinetic energy, 1/2 mv squared, and then so you plug in V equals C, and you can get what Steve said, 2 gm over c
Now
squared.
that's based upon Einstein's field equation, isn't it? I mean, the gravitational metric is partly kinetic energy, is it not, and potential energy?
Yeah.
So,
Mm-hmm.
I mean, these things are all related in some kind of in terms of Newtonian. VSRR83 ask him whether energy density is due to electromagnetic fields caused by gravitation. I think you may have stated many times that only mass causes gravitation, which I have. I have stated only mass causes gravitation.
Well, if you have really high energy density, that
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 is
can act.
mass, though, isn't
Yes,
it?
mass. Yeah,
That's
equals mc squared. Yeah.
mass. I mean, if you think about it, mass is condensed energy, right?
Yeah. Mm-hmm.
So if you have a high energy density, wouldn't that be considered to be mass?
Yeah, even in low energy density, it'd just be a very small amount of mass. But if you're going to be thorough, if you look at the Einstein's field equations, you have this mass energy tensor, this T
Mm-hmm.
mu nu, which is a tensor that includes the mass and energy of the space time that's in that space time.
Yep. And that's why when people are talking about the field equations and the metric tensors, this is what they're referring to. And all like I said, even at the beginning with the equivalence principle, Einstein was trying to relate how you would have this curvature of space time relating to acceleration. That's essentially what he came up with. Which one of the most brilliant things he was saying that if you take this inertial mass, right, and you times it by acceleration, which would be a Newtonian version, he
Mm-hmm.
said, oh, this has to do a direct proportionality between a gravitational field and the gravitational mass. And this was one of the brilliant things that Einstein came up with because he gave a way to actually think about how gravity works rather than just, oh, look, I want to shoot a cannonball in the sky. These are the parametric equations I can use. Okay,
Yeah.
great. But what is gravity? Einstein
Mm-hmm.
explained using general relativity what we think is gravity. And again, I'm a scientific realist. Excuse me, a scientific instrumentalist. I'm not a realist, so it doesn't have to actually be that way. It just has to work. But it sure
Well, this
seems to
is
be the case.
well, Steve. I did want to spend just a brief moment on this because during these flat Earth debates, we have a lot of people throwing words or scientific words around incorrectly, and the law versus theory paradigm is something that is most easily explained in the context of gravity's history. Newton had a law of gravitation. It was a mathematical description that showed the forces between two objects, their some mass and distance between them, and from that you can derive the trajectories and stuff. So that's the thing. A law is, even though the word law sounds like it's unbreakable, it's like proven, it's fact, like it's more of like just a math. It's just a mathematical description of an observation. Think about the law of optics. It doesn't tell you anything about why it's happening or how. It doesn't let you make predictions about anything other than exactly what you've just written down mathematically. It's very narrow-minded and singular, and they have their uses. A theory, in the sense of its predictive power and explanatory power, is more robust than a law. It's more scientifically valuable than a law, in the sense that Einstein comes along and says, "Hey, Newton didn't give us a theory which would explain what gravity is and make all these predictions, explain what's happening." And now we have this curvature of space time sort of paradigm going on to give it a physical explanation. And it has all these predictions. If you do this, this will happen, and you get gravitational waves, which we'll get to in a little while, and all this stuff, right? That took us like a century to test, essentially, you know? And so theory, to a scientist, is more powerful than a law. Gravity is the only scientific quantity that is both a law and a theory. There's the law of gravitation and Einstein's GR. So it's a law and a theory, but a theory doesn't become a law, and a law doesn't become a theory, or vice versa. Technically, if you want to get very stingy epistemologically, the law of gravitation is wrong in the sense that it only works in classical or Newtonian environments, and the low mass density environment where you're not. But even just the Mercury's precession couldn't be explained by Newton's law of gravitation. But hell, we still use it. NASA still uses it to like thread that needle at 3 billion kilometers when you're trying to get like New Horizons to Pluto, to the Pluto system, or anything we've ever launched. We still use it. It works. It's just that we're not in that on that scale where gravity is so strong that relativistic effects come in. You could take you can take GR and do like a limit in calculus, and like it reduces down to Newton's equations and the low field limit. And so you really got to think of it as this like overarching framework that's, quote, more correct, if you will, and that Newton's law was a subset of that. Much like we have quantum mechanics not playing well with GR, they probably marry together under this larger framework of some like quantum gravity or theory of everything, and that when you take the small mass limit, you get quantum mechanics. When you take the high mass limit, you get GR. And so they're bifurcating into these two subsets, which are both equally valid. They've been tested to extremely high levels of precision, at least quantum mechanics has. And then they must live in this larger framework that we haven't figured out yet. That's my spiel on theory versus law. I could go on, but that's all
Yeah,
I
no,
really wanted to make sure I said.
I think it a lot to do with deals with scope more than anything else, right?
Yes.
I don't say that the law of gravity is wrong. What I say is it works for its scope, which would be
Mm-hmm.
kinematics, right? Of course, it's not going to be correct when you're figuring in relativistic effects, but for the scope that what we use it for, and like you said, if general relativity had to explain Newtonian, right? And if you do the limits, you're going to eventually distill down to Newtonian. So the rule of thumb is why use more complicated math to describe the same thing, because it's just going
Yeah.
to limit out anyways.
Yeah.
One of the very similar things in kinematics is that a lot of people don't realize that everybody who's had physics had to kinematics, and you learn what's called parametric equations, and these are parabolic things, right? So we all had that 1/2 at squared kind of stuff, and you learn that, oh, it's a parabolic path. Reality is it's not actually. It's actually an
Mm.
elliptical path because you have two foci, right?
Yeah.
And so there are elliptical equations, but they all will distill down to parabolic equations. So why use them? So the
Mm.
parabolic formulas will model just as almost identical as the elliptical equations, but there's no reason to evolve elliptical equations when you're doing stuff like that because they're going to be the same. So that's why you
Mm.
don't use metric tensor equations to do Newtonian physics. Would you think that's a fair summation?
Oh yeah,
Okay,
absolutely. Yeah.
I mean you could. Why would you? Um, okay, so more questions here. Oh my goodness, people live chat's loving this, and I love the
No,
fact they
good.
love this. They think your mind is sexy, by the way.
Oh well, thank you.
Yeah. Be careful, his mom's watching. Hi, Dr. Kroon's
Ah,
mom. Say hi to her.
hi, ma.
Your son's smart. You did
Mm.
good. Um,
Ah,
let's see here. Let's see here. More questions. I saw them. Here. Is it correct that the gravitational acceleration is lower near the EH of a black hole, event horizon of a large black hole than a small one? So they're asking, is the gravitational acceleration for a bigger black hole different from a smaller black hole for spaghettification?
um, so it's smaller for a bigger black hole because you're further away, but it has the same escape velocity, which is c. Otherwise, it wouldn't be an event horizon.
I think what they're asking is the gradient different because you're going to have less
Oh
of a
yeah, yeah,
gradient toward
mm,
a bigger black hole because a smaller black
yeah.
hole is going to have a very quick small gradient and so you're going to
Yeah,
get
think of it
pulled
as the
apart.
divergence of the field line, like radial. When you draw a small circle and draw a bunch of radial lines coming out from the center, they diverge very largely like that. But if you have like a huge, like that's how like on the surface of the Earth, we're on a globe, right? The plumb line is all like vertical and they're all parallel, or and on small distance scales. And similarly for a large black hole, the tidal forces are going to be small because that divergence is low, the divergence of the field line. So it's much more pronounced for a smaller black hole than a larger one.
Um, Colorado Biker Prepper, by the way, I'm using his motherboard, by the way, so you can thank him for this show because I would never have been able to do it had he not brought me a motherboard. So
Cool.
he actually delivered it to my house. We actually went out and had fun. It was a really nice guy. He asked, can you please give a good description of Hawking radiation? He kind of already did, but maybe you can kind of dive in a little bit more what's happening with the virtual particles on the boundary condition.
Yeah. So everywhere in space, at the quantum scale, is sort of like boiling or teeming with this C. It's sort of like a pervasive probability for a particle pair to just materialize out of nothing. And it's based on the energy time uncertainty principle, the energy time conjugate variable version of the uncertainty principle. And so what that pretty much means is for some uncertainty in energy, you have greater than or equal to h bar over 2 delta t, where t is the uncertainty in time. So it's really kind of cool. The way I like to phrase it, it might be a little bit romanticized, is the whole energy and matter must be conserved that you get like in high school chemistry. That's true only like on macroscopic closed system scales, but at the quantum level you're allowed to violate that, and it happens throughout the universe all the time, everywhere, without us noticing. But the thing that's so cool about it is you can materialize matter out of nothing, so long as you do it within that delta t. The universe is said to have not noticed, quote quote, because then these virtual they always come in pairs, right? And then you have like an electron and an anti-electron that just literally poof pop into existence, but then they're fated to come back together. If you look at their world lines, and they come back together and annihilate and pop back out of existence. And so they do that while they're in existence as virtual particles. They do so for a time duration that's given by the uncertainty relation and the delta E delta T. And so if you could borrow a little bit of time, a little bit of energy for a longer period of time, or you could borrow vice versa. A lot of energy for a smaller time. And so this is happening throughout the universe, right? And even near black holes, because black holes are part of the universe. And you could think of the event horizon as of a given black hole is splitting the universe into two regions. Outside of the black hole, where you're fine when stuff like this happens in YouTube shows, and you have you know, burgers and turtleneck sweaters, and then inside the black hole where like once you're there forever. And right by the event horizon you have these virtual particles popping in and out of existence, and whenever they're trying to do their dance where they steal energy from the vacuum and then only to come back together and annihilate and pop out of existence, one of them, the one that's closest to the event horizon, goes in. It's like, oh shit, there's this strong gravitational field here I wasn't aware of. So it's gone, and then this other particle has nothing to pair up with and annihilate. So and so it just, and since it's further away from the black hole and has some initial speed, it's gonna travel outwards, and the black hole, it's as if that particle stole energy from the black hole due to these quantum effects, and it becomes a real particle with actual like mass and angular momentum and charge, and it travels out into the universe and, you know, becomes part of some nebulae that I take a picture of. And so it's a very slow process, and it takes a long time. But there is an equation I could find. I could pull that up for
You know, I'm so glad you mentioned the energy time thing, because a lot of people know things like the Heisenberg uncertainty principle, right? Most people
yeah.
that have had basic physics understand there's a principle out there that says you cannot know the exact momentum and position of a particle at any given time. You can, if you know the certainty of one, you have no knowledge about the other, and usually it's some kind of in between thing. So as the more I know about the momentum, the less I know about the position, and vice versa. However, that's not the only uncertainty principle out there. There's the energy time equivalence uncertainty principle as well, correct? So that's what allowing for this to occur is the fact that there's a very similar type thing around a black hole, is that if you know more about the energy, you know less about time. You know more about time, you know less about the energy, right?
Right. Yeah. They're called conjugate variables.
And I find that to be fascinating. And by the way, it is weird to think that nature likes to keep its secrets, right? It's like nature can violate its own laws so long as nobody finds out about it. Like it
Yeah.
knows that, hey, we can't let people know about this, right? And real quick question on that. When it comes to like the second law of thermodynamics, right? The second law is primarily saying that as you have these thermodynamical processes, the overall entropy of the universe is going to increase, right? That's a basic
hmm
way of saying it,
Yeah. It's
correct?
like the arrow of time. Entropy overall is always going to increase.
So the directionality of time is based upon the state of the universe from one entropic state to another. As it goes up, that's what we call the arrow of time, right?
Yeah.
Okay. So would you say, because I mean I've looked into this, and I find this to be the case, and yet I've had one person deny this, and I think that they're absolutely wrong. Can we or can we not use multi-domain modeling to apply the second law of thermodynamics to non-isolated cases, which would be the only thing that is truly isolated in the universe? But can we apply it to open systems or closed systems if we treat subdomains as individually isolated and then take a summation or an integral of that system?
Hmm.
Because that the multi-domain modeling to do that is that's how you would actually come and look at a over unity device and say, hey, you look at this over unity device. Yeah, it violates the second law of thermodynamics, which has, again, it's not the universe, but we're using the second law to apply to other systems because of the fact that you cannot put more energy into a system than you can take out. So the second law can be applied to other systems by a technique called multi-level domain modeling. Have you ever heard of that?
Not necessarily. I'm not as familiar with that as I would like.
Landon, have you ever heard of that?
Yeah, and hello.
Hi,
And
Landon. By the
I
way, my buddy. I didn't ignore you today. I thought you were busy. So
no, actually,
you said you're out of town.
I was traveling, right, and
Hmm.
so we just arrived
I'm
in
not
my world
replacing you. You know
line.
that, right? I can
Oh
never
no, no, no,
replace you. I
no,
love you too
no,
much.
no, no,
Okay.
no, no. But our world lines happen to cross,
Right.
so here we are.
Are you sharing?
Um,
By the way, are you sharing for a reason? Are we got something good coming up, or is this accidental?
I'm not sure why I am sharing for a reason. I can stop
There we go.
sharing. There
Okay.
we go. All right. It actually, by the way, it actually ended up showing by default, which is odd. Anyway, back to you're saying about I would be concerned about the interactions of the domains themselves. I don't know how that would be described. Um, so maybe just that I'm not familiar with what it is. I mean, with your concept, because certainly again, the much misunderstood or misappropriated second law really does describe to those systems of domains. You'd have to worry about how the systems actually interact in order to give a if you will, an integral or summation.
Yeah, and so I mean, like I said, I think people thinks in terms of absolutism, right? They think that okay, this has to be, and they look at things very superficially, and then they don't realize there are other ways of doing that. There are other techniques. There are things that maybe they're not aware of, and it's kind of bothersome because again, we talked about theory. And I loved, Dr. Kroon, the fact that you were talking about what a theory is, right?
Hmm.
And no law becomes a theory, no theory becomes a law. They're different things. But the
Hmm.
fact remains for a good theory, if you look into Karl Popper's philosophy of science, it requires a falsification criteria of some kind or more, right? We want to be
Yeah.
able to say, does this theory hold up under all circumstances? And if it doesn't, it's not that great of a theory, right? But
Hmm.
when you hear somebody says, well, the scientific theory of gravity is proven or the theory of evolution is proven, it drives me nuts because no
Yeah.
scientific theory has ever been proven. They're not provable for a reason. You
Hmm.
always want that ability to have falsification. And once you prove something, it can never be disproved. And I see these memes out there all the time. Like I've been in this Facebook group about with atheists and theists since I was in my Twitter timeout right for 7 days. So I was slumming over in this Facebook group, and they didn't seem to understand this fundamental concept of science that, or even math, that you don't disprove things that are proven because they would say, well, you have to prove it first before it can be disproven. Well, no, that's
Well,
not how it
no, no.
works.
I mean, and part of the problem is they're using proof in a different fashion. They might be using proof from a mathematical point of view, which doesn't necessarily translate on to what you're saying, or they're using proven, let's say, in some sort of philosophical sense. But I think the problem is that they don't understand what it means to prove, right? If they did, they wouldn't say they wouldn't say ridiculous things like the theory of gravity has not been proven or has been proven or whatever the thing is. And laws are really good for models, but don't confuse models with reality.
Yeah,
Hmm.
what do you think of like Hawkins multi what is it called? Model dependent realism. Have you ever heard of that term? He wrote about it as far as a model dependent realism perspective would be that these models are useful, they have utility, they make predictions and they explain, but they can't ever be shown to be the way it actually is. We don't know what the territory actually is. We just have a map of it. And I think that's a great way to look at these things like the theory of relativity is that it works. Do we actually know if there's such a thing called space-time? How would you ever validate that? What would you use as a metric to even say there is space time? It just we assume there is because it works.
But is that even a useful question, right? It's because what you're really probably a more practical, pragmatic matter is the model of space time good enough for what we need to do in this situation? Then use it, right? That the same thing, the Newtonian mechanics are good enough to model things like automobile crashes, right? And that kind of kinematics. It doesn't mean that they're wrong. It means that the model has that you can apply it in this area and get reasonable results.
Right.
Hmm.
So does it make you cringe though when people say like relativity is proven? Because think about this: if it's proven, we can never improve upon it. We can never change it. We can never
Yeah, I
add
always
to
say
it.
like all or most of the predictions have been tested and confirmed or whatever. Like the most recent one with the gravitational waves, and we had frame dragging from gravity probe B and all this other stuff.
Yeah.
But yeah, I try to be sort of like a science educator even in everyday life and make sure we're using the
Yeah.
proper terminology.
Yeah,
Yeah, I mean, you say to say essentially that relativity has been well tested and
yes,
survived
it's
many
confirmed. No, I would
very,
say it's confirmed.
very, very, very
Yeah.
rigorous tests,
Yes.
right? Now, this doesn't mean that there isn't a test out there to say, in this area, general relativity is not a good an area that is there. It isn't to say that we won't have some future test that'll show there's a problem with general relativity.
Mm-hmm.
I'd be surprised, and that'd be a really great find. But
But even that happens. Right now, it's confirmed. Now, could it be disconfirmed? Yes, but disconfirmed is not the same as saying it's been disproven, right?
But I don't. I mean, I don't like the word confirmed because
I don't mind it.
Because of the misunderstanding of that term.
I understand the term. I'm fine with the term. I mean, in fact, I think all scientific theories must be confirmed to be a scientific theory.
But if you're a science educator, one of the things you need to be careful of is not whether what you're saying is right, but whether what they're hearing is correct.
See, I take a different approach. I do. I think that it's important to be correct, and if people have a misunderstanding about it, then you can go into detail about it. I don't like changing things to be a science educator, which I'm not. I just happen to like science, but to change it where they get confused. Because when you read these things like from Pop Science, when you read these articles, like I remember one article about 2 years ago. It said black holes. What was it? Something along the lines of science determines black holes don't exist.
Yeah.
Remember that?
Yeah.
Right? And you're,
Yeah.
and you're like, what? You know, but all it was one type through one type of, I don't remember the mechanism because there's, supernova explosions 1A and all that stuff, but they 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 really were talking about a very specific type of black hole, and they didn't put it out that way. And so I don't like the pop science way of explaining things. I try to be precise from a layperson's point of view, but not to be a pendant. Do you know what I mean?
Yeah. Yeah, I see those all the time. They're annoying. They'll say something edgy and almost completely wrong and taken completely out of context just to get. It's like called clickbait. Like, hey,
that's what it is. No, it is clickbait. Not almost like it really honestly is, because they're catering to a person who just wants to go, oh, this is pretty cool. I know nothing about this. Let me check it out. Oh, black holes don't exist. And what happens is you have people that want to promote this false narrative, and they go, hey, look, this article says black holes don't exist. So relativity is wrong. Ergo, Earth is flat.
Yeah, you have a lot of gullible people that don't know any science. They can't think for themselves in these topics, so they're really vulnerable to crap like that. So I definitely have a problem with people pushing out these articles like that just to try to get their ratings up. They're doing a lot of damage, I think.
Yeah, and it's part of the thing again. Is you need to be what I call cringe free. That is, when you're making statements, you don't want people that are quite knowledgeable in the field to go and say that's not quite true. So a statement of relativity is proven correct is something that would cringe on. So, and remember, when you start saying this language, you beware of what people are hearing, not what you're saying. That's an important point of communication, of course, which is why you want to be able to say something like general relativity has survived many stringent tests.
I totally agree, but the problem, I like, for example, like there's this one gentleman, as your favorite individual, Mr. Intelligent Design. I know you love him so much, but he heard one time Michio Kaku say the words gravity doesn't. Let's see, what I'm trying to think. Gravity pushes, not pulls, right?
Yeah.
Yeah, and it was very loose speaking that Michio Kaku was using, right? But now he's trying to go around telling people gravity is a pushing force, and it's just like, that's not how it works. First of all, in relativity, it's not even a force. Gravity is not a force in relativity. It's a fact that you're having a line, a geodesic line going through space-time, and it's taking the shortest distance between 2 points. So it's not a force in gravity. So he's fundamentally flawed from the get-go. But he's just saying, well, Michio Kaku, who is an authority, says this. Well, yeah, but because he was speaking very colloquially and incorrectly.
And there's where you want to be cringe free, and you want to, so that's why I think as in talking about science, you have an onus to be careful about what it is they're hearing, more than say, well, I said it correctly, right? That's now you can't prevent that, but you should be careful about that sort of thing.
I think everybody has a different approach, and I think that it takes a village, right? I think for science education, we have so many brilliant people in our community that everybody does a little bit differently, and everybody has their own thing they bring to the table, and because of that, people have learned. I got to tell you guys, I get messages throughout the day constantly, and a lot of them are things along the lines of, hey, Steve, we have learned so much from being a part of this community. We've learned so much from watching these shows, things they've never been exposed to. That, to me, is the height of what we're going for. You can't ask for anything better as somebody who likes science, or in your case, as science educators, to have somebody say we've learned something.
Yeah, and that's why I'm a Patreon.
Landon is a patron of this channel and of the non sequitur. Well, of this channel, I don't know if you're in the non sequitur, but
I figured. I don't know. I figured. Should I be both?
Well, they're two different things, but I mean, sure. I mean, money's money, right? I live on
I
this.
think
This is my job.
I figured it goes into the same pot. That's why I
Not
hadn't
not
got
this particular
together.
Patreon. This one's separate. I live off this
Okay.
particular Patreon. I haven't gotten a
Oh,
dime from non sequitur yet. We have not done anything for the funds. The only thing we've used as funds for is to help Dave out. Other than that, we have not touched. I have not touched it yet. And Kyle had to dip in a little bit, but I have not
yeah.
seen one penny from that till the end of the year, and I'm fine with
But
that.
see, I've been helping out in directly in other ways. So, but
Hmm.
back to the notion about I think in terms of one of the things that I often find in taxicabs. Taxicabs are supposed to be really good conversations, and someone will learn to say, "Well, you're an astronomer," blah blah blah. Usually, somewhere along the line, I'll get the question, "Do you believe in extraterrestrials?" or something of that form. And here is a case where I think I could give them some information that they're not going to get elsewhere because they're looking for a yes or a no. And so I said, but so I focus on that belief and say, well, why would what I believe have anything to do whether extraterrestrials exist or not?
Well, yeah, your beliefs don't change any ontological facts, right? Your
And
beliefs
there's
don't
another
make
people
a
that says that,
difference.
wow, I didn't think about it. It says, your belief or disbelief in extraterrestrials has nothing to do with whether they exist. So now let's talk about the evidence for existence, and let's talk about probabilities. Let's talk about and eventually, and then we're in a taxi cab ride. I will say I would be very surprised if we were alone in the universe. And here is the data that allows me to feel that way. That's about as
Yeah,
close to belief as you're going to get out of me.
no, that's
Right?
fine. I don't see. Okay, this goes into philosophy, but I have no problem with people saying they believe stuff. We all believe things. Our way of looking at the universe is contingent upon our beliefs. And you can't even have knowledge without belief. You can't say I know this to be the case unless I believe it to be the case first. That is how it works in epistemology. Knowledge is a subset of belief. So when I say I believe aliens exist, there's nothing wrong with that. And they say, well, what's your burden of justification for that? It doesn't mean that I have to prove aliens exist. Doesn't mean I even have to show Dr. Kroon that they do. What it means is I need to justify that I have a rational belief as to why I believe aliens exist. And of course, I would go back to the Drake equation to satisfy that. Do they have to exist? No. And if they do, can you imagine how different they must be from us, or how different, how sane they
But
must
here
be? Is
and here is again back to the thing. I guess and I'm not saying you're wrong, Steve. I'm saying I try to be careful because what they hear is if I'm communicating is quite important if I'm trying to communicate,
sure,
as opposed to someone, let's say like Cy, who just pontificates and doesn't care what you hear, right?
sure.
And this is a case where I am concerned about what it is, what the effect is I have on
Well,
the person.
you have a disadvantage though. I mean, you have an advantage and a disadvantage. You are
Sure,
relatively well known in your fields. You are an expert. You are somebody who's not just your average schmuckatelli, right? So for you, you have to be a little more conservative of your speech. And I get that, right? I'm a
sure.
nobody, right? I mean, I'm only famous on the internet, and even then on a very small little niche of the corner of YouTube. So I don't have to worry about that much. And if people want to ask me, they can just contact me and I'll explain something. So I understand from your perspective, and even from Dr. Kroon. I mean, as a PhD, I think you have an obligation um, to kind of put out good information, but at the same time, you don't want people misquoting you, right? You don't want people want attributing things that you don't actually hold to, correct?
Yeah.
Yeah.
Hmm.
So it is a different thing for you because you guys are well educated. I'm just like I said, I'm just me.
Yeah,
So
but also, I'm also familiar from the world of politics
yeah,
that you will be misquoted. If you say enough to be quoted, you will be misquoted. You
you
will
were in
be,
politics.
and,
You were.
and that's just the nature of society, right?
Oh, I get it all the time. Let me give you an example of being not so much even misquoted, but just completely, just fundamentally taken out of context. Um, I've been on YouTube for I've had a YouTube channel about 5 years, but I've only been having YouTube videos maybe 2 or 3. But have you ever heard me say that I was a theist?
No,
Has anybody ever heard me say I was a theist? No. I mean, my positions are well established.
and
Um,
maybe there's some philosophical dialogue where you say, "If I were a theist, blah 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 blah."
well,
But
that's
I've
hypothetical.
never,
Yeah.
yeah,
Okay.
I've
But
never heard it.
I mean, I don't hold a theist position. I hold an
No,
agnostic position. But I've been like that group that I was in. There's literally somebody who's saying, "Steve, you all the time say you're a theist. You all the time saying, you're a Christian." I'm like, when have I ever said any of such thing? And I actually challenged this person, and I said, look, if you can show one instance of me ever saying I was a theist in a non-hypothetical kind of way, I will donate $1,000 to your charity. That's my life savings right now. I mean, that's literally like my life savings. That's if emergency that I just set aside. I don't even touch that crap, right? I have I made about $100 in my savings account right now, but I have another account that I just don't do anything with. So I have $1,000 in that. So I would donate that to his charity of his choice if he could show that any time I portrayed myself as a theist or said I was a theist. But if he couldn't, he would donate $100 to a charity of my choice, which would probably be the Wounded Warrior Project.
Mm-hmm.
He wouldn't take me up on it. I give him 10-1. But this is what they say. Because he misunderstands what I'm saying, because I say I'm not an atheist, he thinks that translates in his head to, oh, Steve must be a theist. But that's not a dichotomy. And he doesn't understand the philosophical implications that atheism and theism in philosophy is not dichotomous.
Political communication is not to inform. Right. It is to influence. That's a thing you need to understand. So that when you're speaking as a politician, I had to be extremely careful and use phrases whose chopping down wouldn't end up screwing me. So if you did something and say, well, let's take, for example, the person who believes the earth is flat. And then they chop and say, well, I don't know, said the earth is flat. That's what happens in political communication. So you don't say statements like that out of defense. In scientific terms, you could get a little bit better, but still, again, you probably want to use words that are more careful. And I would say also, Steve, one of your hot topics or hot button topics in philosophy, I would not use the word agnostic or atheist with you, because you have a very precise definition, and there's this colloquial misunderstanding. Mm-hmm. And if you try to communicate those things, you will lose the audience or you will be incorrect.
Yeah, well, I mean, but here's the thing. You know as well as I do. I mean, you don't care too much about philosophy, but you're definitely not an idiot in it. But you know I'm not wrong. You just take a different approach, which is fine.
Right? Well, I take a communication approach.
Right.
Let's say this. Steve is correct regarding the physical definitions in his world about what it means to be an atheist and what it means to be a theist and an agnostic, and other things. So you are correct.
Yeah, if you and I went to a lecture course and you and I were going to teach somebody in epistemology and we're going to be the instructor, what I'm putting out is going to be correct, right? But if you go to a group have a communication thing to a bunch of lay people, then I'm fine with what you say. I mean, because I understand you know the difference. That's the big thing. Right, and I don't know how we got from black holes to this, but I'm cool with it. Dr. Kroon is just sitting there going, "What the hell are these guys talking about? I didn't sign up for this. Let's go back to black holes."
But I have to say, black holes are a really great way of introducing people to science. Right? They really capture the imagination. And the thing I wish, however, is that some of the ways that imagination is captured is factually correct. I mean, I remember, we're working with Red Eye and trying to show him what a black hole region would look like, and the thing that's not the whirlpool drain hole thingies.
Yeah.
Trying to give him that.
Yeah, they need to get rid of that mindset that it's some kind of like whirlpool thing. That's completely wrong.
And
these cosmic monsters that eat everything up like Hollywood.
Yes, and that's gives people take those images and extrapolate places where you don't intend them to be.
Yeah.
But even when it comes to black hole and you're dealing with time deals a lot in philosophy, and people don't seem to understand that. I mean, if for example, Dr. Kroon, if I asked you, if all time stopped in the universe, such that there was no change, nothing that we can say from one moment to the next, all atomic motion stopped, all Brownian motion stopped, everything literally was frozen in place throughout the entire universe, right?
Yeah.
Would there even be a concept of time? Because this goes directly to philosophy. It's called reductionism and Platonism with respect to time. And it is a very different way of fundamentally looking at time in this regard. Because if you think time is an actual construct, then if all motion stopped, there is such a thing called time. But if all motion stops and you're a reductionist, you would say, no, there isn't anything called time. It really is a philosophy of how you look at these things. And this is critical when you get into like no boundary proposal, because Hawking looked at it and said, how do I want to look at time? And he looked at it from a very different perspective using imaginary time.
Yeah.
So the philosophy plays a very important part in science, I think.
Yeah, that is something I'm going to think about. I've thought about it before, but it's been a while, and I don't remember what I decided on.
Well,
I go back and
reductionism
forth.
versus platonism. It's hard. It really is hard. No, it's I don't.
Yeah.
And then, you know what's funny? There's no one right answer.
But when you say that everything stops, right? The thing that I would start to say, okay, so everything stops. First of all, I might ask effectively why, which is what has happened to causality, right? If you say everything in the universe stops, then has something come along and changed the laws of physics and causality? You've got two particles, particle antiparticle heading towards each other, and they stop. Photons, do they stop? Because you've got a big problem if photons stop.
You can freeze light. They've actually done that. They've actually frozen light.
No. You can. You're talking about the propagation.
Right. I get you. But here's the thing. I think it's a great question as to why that would happen. But I'm not a big person into causality. I don't think there is a law of cause and effect. I mean, I've tried to explain to people, and I can defer to Dr. Kroon on here because I'm sure he has much more expertise, obviously, in this. But if you have a system that you have no local variables in that system, and there is no information, such as in spontaneous fission or in weak nuclear decay, then there is no causality. There's just...
Oh, no, you could run the laws. You can run any event in reverse time, and it would be indistinguishable. I mean, the laws of physics don't prohibit that. It's just when you get into statistical mechanics that it becomes extremely unlikely.
Well, hang on.
Yeah, but what he said, that's a very important...
Hang on. But if you look at the Copenhagen interpretation, right, there is no local variable model that can satisfy the Bell inequality, correct? There's a global variable model, the Bohmian mechanics, right? Pilot wave theory. But a local variable model saying that there's hidden variables in the system that we are just not aware of cannot exist because it cannot describe all states of the system. So in the Copenhagen interpretation of quantum mechanics, there is no causality for certain events like weak nuclear decay. It just happens. We have no way to determine ever when a particle is going to decay because there's no information in that system to even ever get to make that determination.
That was a big problem for me as in college.
We don't think that way, right? Our brains are hard. Yeah.
I was really solid on general relativity, but when this quantum mechanics stuff started coming around, it's like you got to be serious. And I spent I tell you, I spent a lot of time in labs trying to catch quantum mechanics, right? Trying to show.
So did Einstein,
right? But that's actually it wasn't I said no, you're wrong, or that's there. I said you got to be kidding. And so I went and did what you're supposed to do, test it, and that's a really interesting test. And quantum mechanics of course survived.
Einstein was not a fan of quantum mechanics, right? I mean, he really wanted to think that no information even go faster than light speed, but we kind of find out that local realism isn't really a thing. I mean, we don't know why two angle particles.
What I should have done as a student is said, that's really surprising. Let me check to be sure that's true, because extraordinary claims require extraordinary evidence. So let me go and get the extraordinary evidence. Would be the way I do it now. But back then, and it took me a really long time to get to my head that the universe does not have answers for every question.
And I agree with that. I think we have epistemic limitations, right? And I think that when you leave the realm of science, then you are going to go into philosophical questions. But we have a question in the live chat, Dr. Kroon. You want to kind of briefly explain CPT violations?
Oh, gosh.
That's a hell of a question, right? Can you briefly explain CPT violations? We'll be here for like next 4 months, okay? And especially if you could, maybe try to explain the breaking of the Higgs symmetry, like for the Higgs mechanism, because I even have a hard time understanding the relationship between the Higgs field and the Higgs mechanism to impart mass. If you can try to narrow that down even in a way that I could try to grasp that, I would love that, because it's a very hard thing to wrap your head around.
You guys are testing me a little hard, because it's been so many years since I was working at the super collider and was working in that. Landon, feel free to jump in, but I'll start with I like the Higgs field is a little bit easier than the CPT question because you could visualize it with this the shape of the potential. It's sometimes called the wine bottle or the Mexican hat. Sort of, it looks like a parabola. Then there's like a mini parabola at the bottom, and it's symmetric. So it goes like this, and then there's a hill, and so you have a local minimum at the top of that hill, but it's highly unstable. And in that state, like if you try to rest a marble there, and that's a local minimum. That's its ground. It doesn't know yet that there's like an even lower spot. Yeah. And when it's there, it's highly unstable. You could think about it as even the tiniest perturbation, or even just a probability that it's going to roll to one side, any side, because there's azimuthal symmetry. In that state, as soon as you roll down and go into that little ditch, now you've broken symmetry, and so now you have when you break symmetry in gauge theory, you're going to have terms that pop up that manifest as physical things like mass. In this case, when you break the Higgs symmetry, that potential that's describing the Higgs field, the field equations will tell you that now, okay, now you have a mass. So there's amplitudes and stuff that you have to get into. But it's a great visualization if you guys kind of picked up on what I was trying to describe in terms of the shape of that potential.
Yeah, perfectly.
But CPT, we're talking about charge parity time, right? And when you talk about the symmetry, that there's this time reversal symmetry. So, for example, one of the things that is Feynman Zuckerberg, is that his name? Interpretation that antiparticles are corresponding to particles traveling backwards in time, right?
Feynman said that too, right? I mean,
Feynman, and I remember. So in asking him, I was one of the things to say, do in fact antiparticles travel backwards in time? Is that really what's happening? And he said, well, why? Well, actually, his thing is that that's how we interpret it. Why do you care what it is? Why don't you care what it's going to do and the implications of it? Right? Was the thing. So that was it, because I was hoping he was going to sit there and say, well, no, it's not really. It's just a mathematical trick. It's like, well, why do you care whether that interpretation is true or not? Right? Look at the implications, not is it really doing that?
Well, this goes back to the scientific realism versus instrumentalism, right? This is why I'm an instrumentalist, because I agree with him. Scientific realism, sure, you can believe it, but it doesn't matter. I mean, as long as it's useful, that's all I care about, right? But when it comes to this CPT, would you say, Dr. Kroon, that it's very similar to a metastable false vacuum for these quantum fluctuations, that you have this false ground state that's allowing for certain things, like for example, like maybe the universe to come out of a quantum bubble?
Oh yeah, there's that. Are you talking about that thing where you can have this like wave propagate outwards and like destroy the universe as it goes outward at the speed?
It's called, what is that called? Well, there's the original one that the universe came from, but there's also another model that's very similar, like you're talking about, where the universe can be destroyed, and I don't remember the name of it. It's yes, I know what you're talking about.
The mirror image universe, having a thing where matter can be replaced by antimatter, and you have that way that would essentially go backwards.
That would suck. That'd be a hell of a way to destroy the universe. I'd be like, hey guys, check it out. Oh shit. Well, I mean, obviously it would take time to propagate, but I mean, what would like a big rip look like in the universe?
Oh wow, yeah, that would be crazy.
It would be totally crazy.
But if we can remember, that the majority of these experimental searches for these sort of called lens violations have yielded negative results, and so it doesn't say that that's the way it is, but it certainly appears that way so far.
Well, do you think that these, like for example, dark flow, do you think that's some kind of other universe impinging on ours somewhere? Or if you look at these weird anomalies that we see in space, these anti-entropies of some sort, do you think there's other actual universes that we are seeing an effect from them in any way, or maybe even exist? The universes existed a long time ago, they don't even exist any longer.
It would be hard for me to I find that surprising, given the fact that we don't really see that in signatures in cosmic.
I'll be right back. Hold on.
The cosmic background doesn't give us that thing. We've looked. And there are certainly are ways that we see in the background, but that has to do with sort of the fundamental tones of the universe, back in in time, the time of inflation. Um, so the the thing that but it seems like that it appears that this CPT symmetry, charge parity time symmetry, is a fundamental property.
Well,
That's what it
we know they
appears.
do break, right? We know, especially when it comes to certain things, we expect them
Well,
to break.
charge parity breaks, right?
CP breaks, right? And so we
Yes,
know that happens. We've actually seen that occur, right?
yes, and that was a very, very well deserving Nobel Prize done by showing that sort of thing. So
Now,
there
why?
is,
Why does that break and not time?
and there's that's and in some ways the T was put in there to say,
Fix that
well,
shit.
okay, yeah, so that would be a way of saying so. So
Scientists have fudge factors. See, they do.
but the reason that is coming back to the question that, as a kid, I was asking, that I asked Feynman was, are the positrons really electrons traveling backwards in time? And he was saying, well, that question is not as important. In fact, I remember he said, it's not as important as what is the effect of a positron and how can you model it and what are the implications. Those are the questions that are more important than is it really that way.
Well, yeah, and I think the bigger even question is, why do we have a reality where it is mostly, it's matter dominated? It's not antimatter dominated. In fact, there's very little antimatter out there. Why?
That's a really important question. Where is it? Where is the matter? Where is the antimatter? Right? Is there the most convenient explanation, if they ever come up with it, is that, well, there's some preference for matter, and early on in the universe, in early process of the Big Bang, the matter won, right? But we would then need to see evidence of that asymmetry.
Are they finding that, for example, if you have an anti-hydrogen atom and you have an actual hydrogen atom, are they seeing, other than charge, are they seeing any other difference between them such that they
No, for example, because that's
same,
one of the
right?
big things, that's really big, important tasks that are going on in CERN, was making and playing with anti-hydrogen. And they're seeing now that anti-hydrogen appears to move in a gravitational field just like regular hydrogen. So it appears to have inertia, momentum, all those sorts of things are working the same way with the antiparticles as they are with particles. We're talking about that it's not just that they have an anti-electron. They've taken an anti-proton as the nucleus, and a positron electron around it, made anti-hydrogen, and have kept mounted this around. Again, we're talking about nanoscopic, nanoscopic, picoscopic type quantities, but they've kept it around long enough they can do experiments to see, when you nudge it, does it resist? Does it actually fall in a gravitational field the same way as normal hydrogen? It appears so far that anti-hydrogen behaves like normal hydrogen, except when you connect it with normal matter, it goes poof.
Yeah, and then I read a paper a while back. I don't remember all the details, but they actually measured its atomic emissions.
Sure.
And it was the same. Yeah.
Yeah, and that was a really good test on there. We're talking about the fact that when electrons jump, down and emit a photon of a certain length, those wavelengths are just, within experimental error, just like normal hydrogen.
Well, let me put you guys to the test here, because I ask questions that are not that easy. I like to think, on a little higher than superficial level. So we're going to put Dr. Kroon to the test here. Put him on the hot seat, and you too, Landon, of course. So if you have like an atom, I think we would all agree that the vast majority of space in an atom is just empty, right? It's empty space between the nucleus and the orbitals, 99%, right? Safe thing, right?
Sure.
Kind of not even contested. Okay. Would you also agree that in the nucleus, right, you have these nucleons, and each nucleon is comprised of three quarks, two up, one down, two down, one up, but they're comprised of quarks, right? Now those quarks have to exist in a state where they're not even in existence until they're measured of some kind. Same way with electrons. So there's a probability of where a quark will be inside that photon. So essentially, inside a photon is it's not a photon, it's going to be a proton or a neutron, is empty space, right? So all you have is basically a boundary condition of where you might find these quarks, just like electron clouds. So you have an atom which is primarily empty space, and inside the nucleus, you have the protons and neutrons which are primarily empty space. So what the hell's matter?
Yeah. Virtual, I think one of the ways I like to look at it, even if it might be a little bit romanticized again, second time the show, sorry folks, is that matter is more closely resembles. I mean, it's just like virtual particles and force fields. You know, like when you touch something, the electrostatic forces are repelling, and matter itself is a very, very non-dense, and it's mostly just filled up volumes of just where these force fields and electron orbitals and probabilities are. Virtual particles being exchanged between the nucleus and the electron orbitals. And then you have, even inside a nucleon, you have the much stronger strong force, where you have gluons, which are much higher energy densities, and you have virtual quarks. Even I went to a conference and I saw this whole talk. It was 8 years ago. Forgive me again. The details are rusted away, but he's talking about if you add up the mass of the three quarks, you do not get the mass of the proton. If you add up take into account the energy field of the gluons, you're still not there yet.
Yep.
And then you still got to add in all the virtual quarks that pop in and out of there too.
Yeah, I brought that up one time, and somebody actually told me I was wrong. I told them there's virtual particles inside of a nucleon, and they're like, no. And by the way, they're wrong about that. There definitely is, because I've seen the modeling for it. And you're exactly right. The mass defect, right, in atomic structure, if you took all the protons and neutrons, and I'm not explaining this to them, by the way, I explained to the live feed, because, but to the live feed, if you take the protons and the neutrons and you added them up separately, you're going to weigh an amount. But if you put them together in a nucleus, they weigh a different amount.
Amount.
That's called a mass defect.
Part of, I think, what you were alluding to, the question, the light question was, how big is an atom? How big is a proton? Right? Mm-hmm. And the problem with that question is, well, what is a proton? I mean, you say, well, we got this object here, and we draw this little circular thing, and then color it and so forth.
Yeah, because it's not solid. It's a probability is what it is more than anything else.
What you want to ask, perhaps, is how big is the effect you're looking for?
How big is the radius of where you find the
electron? Well, what is it you're measuring?
I'm
measuring up to some particular electric force. Okay, then the field size of that thing is this big, right? If you talk about what is inside of an atom, and you say, well, there are quarks and so forth. Well, why? Because when we shoot electrons through there, it bounces crazily, and we can get interactions. What we're really talking about is that inside an atom, there are effects, there are forces that we can detect. They're not. Don't think of it as a like a ball of grapes or jelly beans or whatever. Think of it as there's a bunch of effects in there, and the effects have certain ranges. Sorry.
Mm-hmm.
I totally agree with that.
Yeah,
because like I said, what holds that nucleus together is the secondary effects of the strong nuclear force. The strong nuclear force that he was talking about earlier, these gluons that hold these quarks together in a nucleon. But because of that, it extends past the radius of the photon itself, and that's what's binding these things together. So you get this mass defect. So when you do split the atom, the energy that's released is that energy that comes from the difference in mass. And obviously there's an energy mass equivalence, E equals mc squared. So that difference in mass is being converted into kinetic energy when you basically split the atom.
Because you're talking about, again, effects, right? Mm-hmm. That when let's say a uranium-235 atom absorbs a neutron, what are we really talking about? Well, there was a neutron that had an interaction with the U-235 atom. You very briefly create U-236, which oscillates violently, and result in fission, right?
Yep,
And
exactly.
typically, the most common fission is two parts. One, typically about a 2 to 1 ratio. And
Mhm.
if you do all the quantum stuff, you can sort of go as to why. But now you have two very positive charged objects,
Mhm.
the two fragments,
Fission fragments.
in very close proximity to each other, and repulsion causes them to violently
Yep.
apart at an
And and,
enormous,
and they're
enormous
still by the way, they're still vibrating as well. There's kinetic that's what actually makes the heat. Their vibration from that reaction of that fission, they're still reverberating from that. I guess you can say.
yeah.
So
Yeah,
Yeah.
because most of the mass is in that nucleus.
yes,
The electrons just are around for the ride, but the nucleus that fly apart, and that's where the enormous nuclear thing. So again, what you really should be thinking about, and even it's bad to say, well, we had this blob of jelly beans, black and red jelly beans, because obviously the blacks are neutrons and the reds are protons. And you break it apart. That's a deceptive model. If you use that as a physical reality, you're going to run into problems, right?
it's heuristic though. I think it's fine for a basic understanding of it.
But it's a cringeful
The Bohr
model.
model is a cringe, but people still use it, right? We don't,
Yes.
or electrons don't really like go around the nucleus like a planet. It doesn't work that way. It's a cloud actually, and it's a probability.
Yeah, I hate that.
Yeah, but it's easy heuristically to explain to people these are electron orbitals. But if people actually looked at these actual orbitals, they're mind-boggling. It's so confusing how the interactions between these orbitals work. And then when you get into orbital hybridization, it's like, wow.
And
Yeah,
that's a big
actually.
thing about, was also was Feynman was, is there a nucleus that's so large that
Yeah, 137.
the relative effects of the electrons
Mhm.
are get.
Yeah, I think didn't Feynman come up with like the element 137 would be the highest it could possibly be due to relativistic effects of the
Mhm.
electrons.
Well, he had actually had some miscalculations initially on
How
well,
dare
he was
you?
he
How
was just
dare you?
and he later refined them, and now more careful calculations are showing that. But again, it's not that atom goes poof. It's that the
The
effects
relativistic
of the
effects.
relative effects of those the inside orbitals, get to be non-trivial,
Right.
right? The
Which is
chemistry,
which is amazing to think of, though. I mean, that, and
but
not,
the chemistry of relativistic electrons
I
is,
do. I tried looking into it a long time ago, and I was like, this. I'm done. I'm done.
but
There's just
but
no way
but
I could understand
it
this.
would be really nice if there's a nice island of real stability, right? That the next sort of grouping, because there are these, if you will, these the models talk about shells inside atom, and
Hmm.
that there might be another zone where the atoms might become much more stable.
Oh, that'd be badass. Can you imagine?
I would,
Can you imagine a whole new periodic chart?
but the problem, of course, as I say, is that if there really is just beyond our reach a nice stable 130 blah 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 atom, then supernovae would have made it in spades,
Yeah.
or there've been stuff around there, and we haven't seen it yet,
Because the
right?
energy levels that they produce. I mean,
And by the way, seeing is not. I'm not really talking about seeing. We would, if there was some 100 and blah 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 thing, which was a stable transuranic thing, supernovae would have made it, and or neutron star collisions or whatever would have made it, and we would see the signature of that in the light. We would see a spectrum.
Landon
We
gets
would
excited
find
over this
we
stuff,
would
doesn't
find the
he?
helium, right? And we're looking, right? It would be really cool if we did, but we have not found a
Nope.
spectrum of a really heavy atom, unfortunately, out there. It would be
That would
nice.
be awesome, actually. We have a super chat, $5 from
Thank you.
Jason. Thank you. I got a couple here. Can you give a quick synopsis of different interpretations of quantum mechanics? Which is your favorite and why? I've already said that I tend to the Copenhagen interpretation rather than the multi-world, and
Yeah.
I think um, the Bohmian mechanics is fine, but it uses extra assumptions that you don't need to use. So pilot wave theory, yes, it works. I think from what I understand of it, if you want to go into deterministic type of quantum mechanics, but it it just it uses extra assumptions that I don't think that you need to use as opposed to the Copenhagen interpretation. That's just my summation. But I'm not a quantum physicist, so my background was in nuclear.
You're not a quantum mechanic?
I mean, we did. You know what? We don't really touch much in quantum in nuclear power school.
Well,
You don't have to.
once we start giving you fusion reactors,
Well.
then you're going to have to do a lot of quantum.
Yeah.
No,
I'm fascinated by it, but we didn't really, like I said, we didn't have to like go into the different types of quantum things.
I find the Copenhagen interpretation the most amusing, right? Let me put it that way, because the question of which is correct, right? No, it's often the most useful and the most amusing, right? Because it also has for me the most troubling bits of quantum mechanics as well. So that's why I say it's amusing.
What do you think, Dr. Kroon?
I like the Copenhagen just because it's the easiest to explain to people with the double slit experiment. When you talk about that interference pattern turning off when you observe, and it blows my mind. Even if you're throwing or electrons rather one at a time, you wait 10 hours if you want in between each toss, and you still get that interference pattern.
You know, let's table that for 1 second. Because I want to get back to that. Matter of fact, we can
I'll tell you about my experiment on that.
We can do a whole show just on the double slit experiment if people want that one day. I mean, seriously, and maybe we might. If you guys want to see a show on the double slit experiment, comment on this video afterwards. But
Steve, you'll like that because all the philosophy and epistemology and all the science.
And it's weird, right? Reality is weird.
I want to table that because I want to ask some questions on that. We'll touch on a little bit. But 0666 super chat. Are the physical laws time reversible around black holes? If not, shouldn't we expect some conservation laws to be violated too? So is time reversible? The way I'm looking at it is I think the arrow of time as like I said, different entropic states of the universe. So as entropy goes up in the universe through the second law, that's the time's arrow. I never see a point on the black hole where you have a reversal of time. You just have a point where time stops, right? I mean, your space-time, if you look at the Minkowski light cone like this, right, it tips to the point where it's just a time-like journey. So it stops, but it never reverses in any way.
So I like to say that our models break, at the edge, right? And not that laws are broken, but our models, but that's what laws are, is a basic mathematical model, break because they don't handle the conditions at the surface, assuming you understand what a surface is, because a surface is not like the sheen on the billiard ball. It's a fuzzy thing.
It's a boundary condition, right?
Well, yeah, because that's part of the bit is that are black holes hard edge or are they fuzzy? Right? The pure classical general relativity of 1916 stuff would say there is a spot which
I don't think so.
is the thing where the nothing goes.
I go
right?
fuzzy. Are you fuzziest? Right? Are you a fuzziest?
I believe that's one of the important consequences if we actually discover Hawking radiation actually exists, then it'll be.
Well, it would have to be a boundary. I mean, if you have that boundary condition where the virtual particles are being created, it has to be some kind of range, I would think, because I mean, because you have a different x-axis, so you have two photons, two virtual particles may be very, very close to each other, but one still may go in, one go out, and the other one might be off a little bit. It's still going to go in and go out. So there has to be a range, I think, of where the virtual particles can be created, rather than this hypothetical zero-dimension boundary.
The universe is not
one-dimension boundary.
The universe is not kind to absolutes. Right? If you say, I want to absolutely know what the energy is, I want to absolutely know where the escape velocity exceeds c, no, right? The universe is not kind to things that want things absolutely.
So you don't think it's hard-edged?
And so I would be very surprised if it's
What about you, Dr. Kroon? Do you think it's hard-edged or fuzzy?
I think fuzzy because I don't know how exactly, but something with quantum mechanics is going to make it some uncertainty there in its thickness.
Good point. Yeah. I mean, just the uncertainty itself is going to make some kind of fuzziness, right?
And that's part of the essence of Hawking radiation, right? Yeah. And it's one of the important points. And there is the next generation accelerators. Are what are the goals as to whether or not we can produce atomic scale black holes, because it would be really nice to see those black holes decay and accelerate. It's not going to swallow the Earth, right?
No.
If we manage to, if it's possible to create them in an accelerating an interaction, then they're going to decay faster than a photon can get there, right? But the decay modes of things that form these macro black holes are going to be really weird.
Do you know what's more dangerous, I think, than a black hole being formed? Have you ever heard of something called a strangelet particle? Strangelets are particles being created with this. I'm old school, right? I'm older than you, Dr. Kroon, but I think Landon's got me a few years, but not by much. No, actually, I don't know who's older, but we're about the same age. Back in the day, we learned it as up, down, strange, charm, beauty, truth. Now they have up, down, up, down, bottom, top, beauty, truth. Is that what it is?
Yeah.
But there's particles, these quarks called strange quarks, and they would form strange particles. And if they were positive, they would have an attractive force. And so they were theorizing a long time ago, if you formed these strangelet particles, it would be like a gluon ball, and it would just make everything matter, just destroy it completely by converting everything into these strangelets. And there was actually a show based upon this a long time ago with Peter Weller called Odyssey 5.
But those conspiracies no longer are around, just like polywater, right? No one talks about
polywater. I don't necessarily believe the conspiracy stuff, but this was actual physics. I mean, it was based upon things they were conjecturing at the time. Now, I think they've determined that.
Dr. Kroon, did you hear about the polywater thing?
No.
Was that under certain conditions, water molecules would form along polymer. And once you started this thing, it would other water that would come. Other water that would connect it would just continue. And if you created polywater and dropped in the ocean,
isn't that from Slaughterhouse 5?
Okay.
But
it sounds like Kirk Wagner to me.
Yeah.
But whatever.
But back to the thing about universe turns to be not kind to people that want absolutes. And by the way, watch out the folks that are doing for religious folks that want to have these absolutes, right? Universe is not kind to you. It's certainly not kind in the mathematical sense, and it's not kind to you in the physical sense of saying absolute knowing what it is. That's one of the essence I think that's hard for people to understand about the double slit experiment, is that there are questions you can ask which the universe won't give you an answer. There isn't an answer.
Well, you know what? Let's kind of leave that for another time. I'm going to touch on it real quick because we're going to be ending this soon with the double slit. And by the way, if you guys do want to see that, mention it in the comments section after this video is done. But some interesting things with the double slit that we'll get into is exactly what Dr. Kroon was talking about. Think about this, people. Normally, if you have a wave, right, and you have an ocean wave passing between an open thing, you're going to produce these special waves that you can actually see. You can actually see them come out, right? So you'll see, even if you have these parallel lines, you're going to produce a wave front through that opening, right? Everybody kind of seen that. But here's the interesting with the double slit experiment. If you model it as a particle and you shoot an electron through that opening, and you just do it one at a time, doesn't matter if you do it 5 minutes later, an hour later, it doesn't make a difference. You're still going to see these interference patterns that you would normally see, like the ocean. You would see the interference patterns when you have a slit. So the double slit experiment, when they first did this, they were like, what's going on here? Because we don't expect interference patterns from particles. You expect them from waves, right? You have degenerative and constructive interference, but you don't have that with particles. That's what makes the double slit experiment so really cool. And these weird trajectories that the path of these particles take are just bizarre.
So I had a really it took a long time in college, but I built an experiment where I used copper sulfate impregnated with very trace amounts of radium, and the decay, you get a beta decay, it would come out, and as the electron, the beta particle is going through the cubic sulfate, it would disturb the crystal, right, and break the crystal. And they had a double slit and a zinc sulfide plane on the back, and so I'd wait until I'd see a flash that was evidence that basically the beta particle had hit the spot. And then I would pull out the crystal, and I would look for under a microscope. I look for the path, and said, okay, I had one radioactive decay, and there's the path it started out. I could see it ripping through the crystal structure, right? It's like a bullet go there,
It's like a
and
like
it went through the double slit experiment. And so I only pay attention to the spots where I could say only one particle decayed, only one particle left. I knew the beginning trajectory, I knew the end result, and be damned, it was double slit in an experiment. That is, the incorporated interpretation is the particle interfered with itself.
Weird.
And that was back to the professor sit there and say, stop talking about where is the particle as a point in a graph space. Start talking about the effect, right?
Bizarre, isn't it, though? I mean, how that...
But it was really, and it took me several weeks of doing this stuff and building up enough of a histogram where I only took the case when it was one electron being ejected from radar.
But even with one electron, I mean, okay, if you look at somebody had asked about different models of QM. If you look at the pilot wave theory, every trajectory is accounted for. It's hard to determine it at that point. It's just one particle, pick one, and it's really contingent on the integral. What is it? The path integral formula, right? Which, by the way, people who want to look at some bizarre stuff, go look at the path integral formula. It is trippy.
Yeah, right. But I was saying, I had this, I had the crystal, and I could say it came from there, and I could see this line. I could see where the beta particle came out of the crystal, headed towards double slit, and some went on the thing, went in that spot, right? I could then do that mapping, and so I was assured I was only paying attention to one electron at a time.
But it still produces an interference pattern with multiple electrons.
It did not create shadows. It created experiment.
And you're trying to disprove quantum, and you're like, damn, right? So
yes.
Well, I want to thank you guys. It is time to bring this to a close. This was great. I know we didn't get too much in depth in the black hole, which is fine. I mean, I don't know where the boundary is for where we want to go as far as being too technical and not.
The problem is that once you go in there, go down that rat hole, you never come out of the black hole.
Yeah, that's the downside, right?
Unless of course you're Hawking radiation, in which case the question about is entropy conserved or not? That's
is information or entropy?
Is information conserved?
I think it's an entropy. Yeah. See, I tend to Susskind, by the way, who I really want as a guest, and tend for somebody out there that knows Susskind.
We're trying.
But I mean, I'm fascinated by the fact that it's a firewall paradox can kind of be resolved in a way, in a very intuitive type way, I think. That it's both. It is conserved. I think information is conserved. Do you?
Yeah.
Well, there you go.
I'm not sure that Hawking should have conceded the bet.
Wow. Again, it's an interesting thing, right? I would love to have Susskind come on and actually talk about that bet and actually come on and explain what was really the topic of why do they think that information is conserved or is not conserved? Well, and more fundamentally, because, Landy, you were talking about earlier, why is the case? Why is it the only three things that are conserved in a black hole are charge, angular momentum, and mass?
What's the reasoning for that? And so the bit about it saying is that, have we had the experiment to show that information is conserved going to black hole? No, we haven't. Right? We don't have so.
But it's highly suggested, is it not?
It's expected, but your expectations don't fit reality, like the double slit experiment.
Boy,
right?
ain't the story of my life.
The universe doesn't care what you expect. Doesn't care about your model. It does what it does and doesn't ask your permission to do what it does. So for us to say, well, of course, in order for quantum mechanics, blah blah blah, we can't lose this information. Like, okay, prove it, right? That's the thing, and that's why I would have instead said, we'll put this set of encyclopedias under a glass case at Cambridge, and maybe some future centuries down the road, someone will do the experiment, and the case will be awarded possibly to the.
Reality doesn't care about your fifis.
So that's really, I think, it's important for people to quite understand.
I agree.
When you talk about models, theories, so forth, what you want out of the universe is doesn't really hill of beans as far as what the universe actually does. So what happens in a black hole? I mean, now I'm also one of those people that question whether or not there is a singularity inside the event
I'm
horizon.
not a big fan of there actually being one per se. I think it's more of a mathematical thing. But again, I'm just a nobody.
What
Whether
do
I
you think?
like
What
it,
do you think?
but
What is there really a singularity down
No,
inside?
I'm a big proponent of this idea of there being a string there.
yeah, I can
Like
get that.
Okay.
the
Yeah,
toroidal. We were talking about that before you came
yeah,
on, and I think
I
I
agree with
like
you.
there being a string there, a closed string.
I think
It'd be
that makes a
amazing
lot of
physics
sense.
inside there. I'd like to
Well, I mean,
propose.
think about. Because I'm trying to picture what you're saying. Because a long time ago, when I was in high school, I actually went to a seminar on closed timeline theories. As I was like 16, but I happen to like black holes, and I went to a seminar, and I do remember some parts of it. And I think if I can picture what you're saying, the singularity itself is literally like you're saying a string that's enclosed in itself, such that there's nothing that ever goes beyond that to the reality. I mean, it
Mhm.
is encapsulated into itself, right?
Yeah.
I mean, that's a fascinating thing to think about, a closed timeline like that.
But who's to say that there isn't another effect at a higher density that takes over and says, stops, just like the effects at a white dwarf
Well,
level
you never
to a
you
neutron
never
star
know.
level, that there isn't something else beyond there that stops the infinite point process. And I think if I mean, it would, to me, it would be surprising that, oh no, you get some infinitely dense something or other down there. That seems to be that would be surprising to me.
But do you ever know base level? I mean, do you ever say that this is our base level reality? And by the way, I remember this. You're talking about the Tolman Oppenheimer Volkov limit
yeah,
for
yep.
white dwarfs, and you're talking about the Chandrasekhar limit for neutron stars, right? Or do I have that backwards? No, wait.
Yeah,
The
Chandrasekhar limit
for white dwarfs, and then the neutron stars, it's the Tolman Oppenheimer Volkov limit. I always get those
yeah,
confused. But anyways,
yeah.
for electron degenerative pressures, right?
Yes. So the question is down beyond the event horizon, what is the state of matter and energy down there, right?
Isn't
And
astrophysics fun?
and I don't know that you can just say, well, the mathematical models say you got an infinite point size, because for one reason the mathematical models really break at the edge, right? So at the event horizon, wherever that happens to be, in a fuzzy spot, you're already broken. So what makes you think you can then extend your models inside and say there's a point,
Right.
right? Um, who's to say there isn't another state of matter down there? Because, by the way, there's lots of states of matter, it turns out. The universe likes to make new states of matter. So
We're
why
discovering
isn't
new
there
states of matter all the
another
time. Dense
weird
matter
state
and
down there that halts the collapse or whatever, right?
totally.
Don't assume, particularly your model breaks. I mean, again, that's what bugs me. The models break at the edge or the boundary region, the event horizon. So what makes you think you can do something inside and be confident?
Well, we're gonna leave it with that. But Dr. Kroon, you want to leave us any parting words of wisdom? I'm actually gonna do a transition, so this is gonna be playing music while we talk here. They can hear us, but I gotta call it quits. So I'm gonna be transitioning it out while he gives his final summation on this. What you think, Dr. Kroon?
Yeah,
Talk to us about black holes and what you think, real quick.
I'll just say, I'll give you the PBS special. Black holes are in the development of human understanding of them right now on a continuum of our understanding that is constantly evolving and has been for hundreds of years, from the first mentions in the literature of things that we now call black holes, and our understanding will inevitably, in my opinion and personal belief, push forward despite the current and extraordinary challenges that are presented from these exotic objects, nature's little secrets. And I look forward to hopefully living long enough to see more from these black hole astrophysical cosmic objects. And I can only imagine, and my imagination is probably not even enough to glean from what nature has in store for us. So stay tuned, folks, and watch the news.
And I couldn't agree with you more. And with that, thank you guys for watching. Leave your comments in the video description. Like, subscribe. Patreon is in the video description as well. And share these videos. We do appreciate it. And we'll see you next.